Okay, so the next talk is on testing matrix product states, and the speaker is Mehdi.
All right, do you hear me? So thanks for coming to my talk. This is joint work with John Wright, and it's about testing entanglement in pure quantum states. So as we all know, the state of n qubits is a vector in a tensor product of n d-dimensional complex spaces. And a given many-body state could be either entangled or product. So if you can write a state psi as a tensor product of n single qubit states, we call it product. Otherwise, there are states that you can write it or factor it this way, we call these entangled states. So given this, there are some natural questions we can ask. For example, if a given state psi is entangled or product, or if it is entangled, how entangled it is. So thinking about these questions has been influential in quantum information and quantum computing, both conceptually and practically, starting most famously with the Bell test. There have been many applications in interactive proof systems, quantum cryptography, and problems in computer science like tensor optimization. And also thinking about entanglement has been very insightful for understanding the physics of interacting quantum many-body systems. So in this talk, we're going to look at these questions from the statistical perspective. And as you'll see, there are very simple and natural questions here that we still don't have good answers to. So the way we're going to formalize the questions I had in the previous slide is using the property testing model, which is a widely used model in computer science to test a property of a set of objects, which in our case is the set of pure quantum states. So we'd like to design an entanglement testing algorithm that when given multiple identical copies of a pure quantum state psi, performs a measurement on these copies. And if the state psi has at most certain amount of entanglement, then this algorithm accepts with probability at least 2/3. But if the state psi is far from states that have certain amount of entanglement, then this algorithm rejects with probability at least 2/3. And our primary goal here is to find the fewest number of copies, known as the copy or sample complexity, needed for designing reliable entanglement testing algorithms. So we eventually also care about the time complexity, which I'll get back to it later. So there are two vague things in this model that I need to clarify. One is, what do I mean by a state having certain amount of entanglement? How do we quantify many-body entanglement? And also, what do I mean for a state psi to be far from the set of entangled states? So let's just start with talking about one way to quantify many-body entanglement. And in our work, we use matrix product states to do this. So suppose you have two qubits. And as I mentioned, their joint state is a vector in a tensor product space with some complex amplitudes aij, which I now assume these complex amplitudes have a specific form. They're trace of some complex matrix ai times some other complex matrix bj. So we have a total of d of these A matrices and d of the B matrices. And one important constraint I'm going to impose on these A and B matrices is that their size is at most r. So given this, we get a set of states, which we say there are matrix product states with bond dimension r. And for sure, I'm going to show them by MPS of r. So one example is when we have a product state. So in this case, these A and B matrices are just simply complex numbers, and therefore bond dimension is just equals 1. You can have a Bell pair, and for that, you see that we need these 2x2 matrices to generate the 1/√2 amplitudes. And more generally, any bipartite quantum state can be written in the MPS form if we allow the bond dimension to be as large as the qubits dimension d. And so this is attained by this simple example of the maximally entangled state on the slide. And as you see, bond dimension is kind of limiting the amount of entanglement present in the bipartite state. When the bond dimension is 1, we have no entanglement. The state is a product state. As the bond dimension grows, we can express more and more pure quantum states in the MPS form. So all of this also generalizes to the general n qubit case. Now these complex amplitudes in the state are trace of some n complex matrices multiplied together. And again, we're going to assume that these A matrices are, their size is at most R. And as before, if we allow the bond dimension to be large, now exponentially large in the number of qubits, any quantum state can be written in the MPS form. But for limited amount of bond dimension, we are restricting the amount of many-body entanglement present. So I won't go into details, but turns out quantum states that are, matrix product states with a small bond dimension can capture physically relevant quantum states that show up, especially when dealing with a chain of interacting quantum systems. So they're widely used in physics and condensed matter as well. So there is an alternative characterization of MPS that we're going to use later on in this talk. And this characterization is in terms of the reduced density matrices we get over contiguous cuts of this many-body state. So we're going to look at the reduced density matrix we get on the first qubit, or on the first 2 qubits, or the first L qubits, and so on. And MPS corresponds to the set of states whose these density matrices they have has a rank at most R. So rank meaning the number of non-zero eigenvalues of these density matrices is at most R. So have this characterization in mind. We're going to get back to it later. Okay, so having defined matrix product states, let's go back to testing entanglement. Now, instead of this initial property testing model I told you about, we can be more specific. Now we'd like to design MPS testers, which is an algorithm that when given sufficient number of copies with high probability correctly detects whether an input state psi is an MPS with bond dimension R, or whether it's delta far from being MPS R. So the only remaining ingredient I need to tell you is what do I mean by being delta far from MPS. There are 2 natural ways to define this distance. One is to look at the maximum overlap between psi and the states in MPS R. And the other is to look at the minimum trace distance between psi, now thought of as a density matrix, and the states in MPS R. Both of these are related to each other, as you see. And I'm going to switch back and forth between them throughout the talk. But I'll reserve delta for when you're measuring distance according to the trace distance. And as I mentioned before, given the number of qubits, the bond dimension, and a distance delta, we want to find the minimum number of copies for having such a MPS testing algorithm. So now let me tell you about the case that we are testing product states, meaning MPS testing with bond dimension equals 1. So I'll tell you first about a 2-copy version of this test, but later we see how we can boost the performance of this simple test by performing it a bunch of time on parallel copies. So this 2-copy test was first introduced by Minter et al. And then rigorously analyzed by Haro and Montanaro. And its main ingredient is the swap test. So you might be familiar with this already. Swap test is a 2-outcome projective measurement that takes 2 pure states as input and outputs either accept or reject. So accept is, it corresponds to when we have the projector pi swap, which is identity plus the swap operator over 2. And you can show that given psi tensor phi as input, the swap test accepts with a probability that relates like this to the overlap between the input states. You can generalize this to the case of mixed states as well. And in particular, if you have 2 copies of a density matrix rho, then the acceptance probability relates like this to the purity of the input state. So having the swap test, now the product test proceeds as follows. We perform the swap test on each qubit and its copy. And we do this for all the qubits. And we say the product test accepts if all of these individual swap tests accept. So this is the test. And turns out if you input a product state to this test, it just passes with probability 1. And the reason is simply because each of these swap tests we are performing is given 2 identical copies of a pure state. And based on what I said earlier, it just passes. But more interestingly, it turns out if you have a state that is delta far from being product, then this product test rejects with the probability at least delta squared. So this is shown by Hara and Montanaro. And the intuitive reason behind this is that if the state is far from being product, it means some of its subsystems are mixed states. And therefore, the sum of the swap tests we are performing will reject. Again, based on the acceptance probability of the swap test being related to the purity of the input state. So if you repeat this 2-copy test on 1/delta squared pairs of qubits in parallel, you can boost its performance in this delta squared probability of rejection to 2/3, which is what we initially wanted in the property testing model. And one interesting application of this product test, or the soundness of the product test, also shown by Hara and Montanaro, is that the complexity classes QMAK and QMA2 are equivalent for k greater than or equal to 2. So what is QMAK? It's the class of problems solvable by a polynomial time quantum verifier with the help of k unentangled provers. So this equivalence between QMAK and QMA2 has applications in improving hardness of approximation for some tensor optimization problems. So you can see a list of almost 20 of these problems in the paper of Hara and Montanaro. So the original analysis of the soundness of the product test is rather elaborate, and it's been open whether there is a simple analysis of this test that also improves its performance. So this brings me to our first result where we achieved this. And the proof is very simple. It fits into one page. You can see our paper for the whole proof. I'll just sketch it briefly here. And the first step in our proof is to perform the Schmidt decomposition of our many-body state over the first cut. So this gives you this expression for the state psi in terms of these Schmidt coefficients lambda 1 through lambda d. So these form a sorted probability distribution. And if the state psi is known to be far from product state, there are basically two cases. Either the largest of these Schmidt coefficients, lambda 1, is small. And because these lambdas are sorted in a non-increasing order, this means the whole distribution of lambdas is rather uniform. And therefore, the first qubit is highly entangled with the remaining n-1 qubits. Therefore, the first swap test that we're performing with good probability detects this and will reject. So the other case is when lambda 1 is large. So let's assume it's very close to being 1. And in this case, the state psi is roughly equals to A1 tensor B1, where they're obtained by the Schmidt decomposition, and B1 is a vector on n-1 qubits. So as you see, there is no entanglement between the first subsystem and the rest in this case. So the first swap test just accepts. But for the state psi to be far from being product, it has to be the case that the state B1 over the remaining n-1 qubits has to be far from product. And because of this, the remaining n-1 swap test we're performing as a part of the product test with high probability reject. So this rough idea can be made precise using an inductive proof, and it gives us this probability of acceptance or rejection of the product test in terms of delta squared, the distance of the state to the products. So this bound that we get is actually tight when delta is less than 1 over square root 2, and you can show that using the simple state you see on the slide. So this settles the performance of the product test for this regime of parameters. Now I'll move to our second result, which is testing MPS for any arbitrary bond dimension. And our main ingredient in this test is the rank tester due to O'Donnell and Wright, which is an algorithm that when given multiple copies of a density matrix rho, decides whether the rank of rho, the number of non-zero eigenvalues of rho, is at most R, or whether rho is epsilon far from being rank R. And they managed to pin down the copy complexity of this rank tester, which is R squared over epsilon. So they use a generalization of the swap test in their work called the Vickscher sampling. And they also show that their test is the optimal test among all rank testers with perfect completeness. So one other thing about this rank tester is that it can be efficiently implemented on a quantum circuit of size polynomial in the number of copies and logarithmic in the local dimension D. So this also implies that the MPS tester that I'm going to tell you soon about can also be efficiently implemented on a quantum circuit. So what is our MPS tester? So recall that I mentioned the set of MPS can be captured using these states whose density matrices across different cuts has a rank of at most R. And our test basically checks this condition. So we perform the rank tester I mentioned in the previous slide over all the cuts of the state. So we perform the rank tester on the first qubit and its copies, then on the first two qubits and their copies, and so on. And we say the rank tester, MPS tester rejects if all of these rank testers, if any of these rank testers we're performing reject. So this is a very simple test. And we can analyze its copy complexity by giving both upper and lower bounds. So we have an upper bound of order n on the copy complexity, and its proof is simple. I'll just sketch it here. And it relies on the fact that if a state psi is known to be far from MPS of bond dimension R, it means there exists a cut in this state such that the reduced density matrix across one side of this cut is 1/n far from being rank R. So now if we give sufficient number of copies to the rank tester that is being performed on this cut, with high probability we can detect this. But of course, we don't know where this cut is located, and we're performing a rank tester over all the contiguous cuts of this state. But turns out these rank testers we are performing mutually commute with each other. So in particular, the order that they're applied doesn't matter, and they form a valid quantum measurement. And you can think that the first rank tester we are performing is being performed on the cut that is far from being rank R, and therefore we detect. So this is a rather pessimistic analysis. You can ask whether we can improve this analysis to show a constant copy complexity for MPS testing for any bond dimension, as we had in the case of product testing. So this actually is the case for a class of quantum states known as the bunny state. So you should think of the bunny's ears as 2 1s and the grass as 0s. And the state is a superposition of the bunny hopping to the side. So you can show that this state is MPS with bond dimension 3. And with more work, you can also show that it's actually constantly far from being MPS with bond dimension 2. So we show that if you run the R equals 2 MPS tester on this state, which we know is constantly far from being MPS 2, if you run the R equals 2 MPS tester on 3 copies of this state, it rejects with probability at least 1/6. So you get a constant copy complexity for this specific choice of a state. And so this is nice. For a while, it made us think this should be more generally true. We can find a constant copy complexity for any quantum state, but now we know this is not the case. So we have a lower bound of a square root n for testing matrix product state in general. So I don't have time to go through the details of our construction. Let me just briefly tell you what is the hard example. So it's this state psi and any other state that can be obtained by performing random local unitaries on this state psi. So we feed a random ensemble of a state to our MPS tester. And this state psi, as you see, is a tensor product of a bunch of bipartite states phi, which are designed to be 1/square root n far from MPS R, such that when you tensor them together, the state psi is constantly far from being MPS R. But when you apply these random local unitaries on the state psi and then feed it to the algorithm. So first of all, the distance doesn't change. These local unitaries won't change the distance of the state to MPS R, but they manage to confuse the MPS tester unless you give sufficient number of copies to it, which turns out to be square root n. So this is the rough idea for the lower bound. And that's all I wanted to tell you. In summary, I talked about statistical tests for testing many-body entanglement using matrix product states. I gave a simple and improved analysis of the product test and gave both upper and lower bounds on MPS testing for any bound dimension. And one thing I forgot to tell you is that our lower bound applies not only to our MPS testing, but to any MPS testing algorithm. So these are some open questions left by our work. One is to, of course, find a tight copy complexity for MPS testing, whether our order n upper bound is tight or square root n lower bound. We can think about testing other families of states, like other tensor network states or states generated by low depth quantum circuits. And all I told you was about pure quantum states. We can also ask if we can test mixed entanglement in mixed quantum states. And this is widely open. We don't have any algorithm, even for the simple case of a bipartite mixed state, to see if it's a separable state or not. And that's it. I thank you for your attention. Sure. There is an online question before the audience asks their questions. They ask, are rank testers efficient to implement? Also, do these techniques help to learn an MPS? So yes, as I mentioned, we use the rank tester of O'Donnell and Wright, which can be efficiently implemented. We perform n such rank testers, therefore our algorithm can be also efficiently implemented, but we do use entangling measurements. So it won't be easy to implement these tests in practice, but there are, you can run them in polynomial size circuits.
Learning? They asked if you can use.
Oh yeah, for learning, yeah. So there are already learning algorithms known for MPS. It's in a paper by Steve and his co-authors. I don't know if they achieve the optimal scaling for learning MPS, and the optimal scaling should be of the order of number of parameters which you want to learn. So if for MPS is the number of qubits times d local qubits dimension times bond dimension squared, and you know, assuming you have that, you can use it to test whether your state is MPS or not. But it would be an order of local dimension d worse than our order n upper bound, which and our upper bound might be loose by itself. Whether you can use MPS testing to get learning, you could, but then there are also simpler ways of getting learning without going through our testing algorithm, simply by using the tomography or the learning algorithm combined with a swap test, and then doing binary search to see what is the rank. Okay.
Thanks for the nice talk. So one generalization of this might be, you can think of a matrix product state as having a bound on the entanglement rank, but you could ask for bounds on entropy instead, which would be, I guess, a different promise on the set. Have you thought about that as a possible generalization?
So we don't have it in our paper. It's a valid question. There are known algorithms for testing the entropy or generally other properties of the spectrum of a quantum state. And you can usually think of generalizing this by basically performing these known algorithms on different subsystems. And you know, you get a testing algorithm. The interesting question is if you can do better. So that's we don't achieve this in our paper. That's our order and upper bound. You can do it for product testing, but it remains an open problem that we don't resolve. But it's a very good question.
Thanks.
You're welcome.
Thanks for the nice talk.
Thanks.
Another notion of entanglement is the tensor rank. Have you thought at all about maybe generalizing this to detecting high tensor rank at low tensor rank?
That's also a very good question. We don't do it in our work, and I don't have a good idea how you would do it at all. So like that's like an open question worth thinking about.
Thanks.
You're welcome.